Alright, how are we doing, everyone? Welcome to the EE360 Signals and Systems. I'm going to be going over impulse responses, which is basically, it will show you the following. So suppose we had, a system, H of, and we're going to go into the discrete domain. It's much more easier to explain this, which will have some input. We don't even know what this input is. X of n spits out some output, y of n. And from what you've learned in the lectures, from Dr. Sears' lectures, is that y of n is equal to x of n convolved with h of n. And h of n is our system response. It's our system, something that we can build with, op amps and delays and samplers or whatever you want to call. So the more important thing is, okay, so we have an output right here. Circle it in green. This is our output, which is going to have, some values. And then this input is going to, correlate with this output. It's going to generate some outputs. However, we have this term, which we will call the impulse response. So what is the impulse response? What you're probably going to say. So suppose we introduce our little friend, Running Man. And suppose he had, some big boots. And he just kicked the system. He just kicked the system. So right now, what we're trying to figure out is, what does the system do? Is it going to go, go crazy into, infinity, or is it going to go, start off pretty slow and then, slowly decay into something that we really like? So for stable systems, as you can see, we would like to have this situation. So this situation is basically what happens when we kick this box, kick this system. And what we would like to see is, a nice sync response. These little wiggly guys that you can probably see everywhere, especially in your sync filters, your bandpass filters. But point is, this is what we want. It's the natural response of this impulse response. It's basically, what does the system do when we just kick it? And another theory we can think about is, suppose we model the kick. So this kick is actually what we can call, our Dirac delta, or Kronecker delta, because we are in the discrete domain. So if we want to treat this x of n is equal to this, then we can just do Dirac delta of that. Kronecker, sorry. And what did you learn from, signals and systems when you convolve, the Kronecker delta with anything? You get the anything. So this is literally what you're looking for when you're looking for your impulse response. So if you just kick your system, your output is literally going to be your system. This is the most, this is the best concept I can probably show you right now. And this is a really important factor when you go into signal processing. So let's go bring out another thing to explain with an example. There we go. Actually, note for quality's sake, let's do this. Let's bring out a piece of paper. Now, let's say we build some system. Your professor gives you some system, alpha, can't see that, there we go, and minus 1 is equal to some inputs plus b of x and minus 1. So you can note that we have some memory, and one thing I want to show you is, we don't know what this system does, but maybe you do. If you do, that's good. That means you're following. Is this class hard? No. Ah, perfect. So y of n is going to equal x of n plus beta, that we just defined, at minus 1, minus alpha y of n minus 1. So let's build it, because we don't know what's going on. We're just saying, all right, we have some system. We just don't know what it's going to do. We have an output. We have inputs. Let's solve it in terms of our current outputs. If you have some gain factor here, some coefficient, just make sure you factor that out into everything. We're just practically doing this. If I were to give you a quiz on this, everyone should be able to get this, right? And actually, everyone should be able to draw what we're about to do right now, which is, suppose, let's see, we have our input. And now we're saying, okay, how do we do this? We're gonna do a direct form 1 block. This is the way you go with direct form blocks. One, you draw your wire, and then look for memory. Here's your memory. Then we design these memory blocks. This is for visually easy for me to explain. So we have some delay, then we have some gain, star gain, and then we have a gain right here. This output input goes directly into the output. Let's do this for clarity's sake. Plus, so let's draw our arrows. And this right here is our feed forward path. This path goes forward. So if I were to, bring our little running man back, and he were to, kick this system with his big old boot, that if we have a 1 here, this 1 at time equals 0 is right here. This will immediately fall through here. However, now if at the next clock cycle, now this one's right here, and this feeds right into the next step of the system. So this right here is the kick. This 1 will literally go through our system. So if I were to tell you, all right, design me a feed forward path, or I'll explain later, like our feed forward path for a direct form 1 block, everyone should be able to get this right here, right? Yeah. All right, perfect. So the next thing we want to focus on is, well, we have this, Y term. And we know how to deal with this. So the next thing you should naturally do for a direct form 1 block is, okay, we just finished our inputs. They're going through, and they're turning into some, node C of n. This is for analysis purposes. If I were to destroy this, then our output is literally C of n is literally equal to Y of n. So we're done with that. So if we were to analyze just this, that would be our final answer. Now, to take into consideration this memory, let's draw this. And now, okay, we have some memory, or delay, or D flip-flop, or whatever you call it, whatever you would like to call it. It's going to have some gain factor. So this output sees a negative alpha. Okay, this is how you analyze. Like, you're trying to figure out the signs on these, and you're like, oh my gosh, I don't know. Look at our output, walk backwards. So we're walking backwards. I'll just draw these arrows so that it's easy to see. And we have a negative. Alright, so if I were to tell you, we're given, the following LTI system, a linear time invariant system, everyone should be able to do this. Alright? This is all trivial, so if someone were to come to you and say, hey, draw me a direct form 1 block of this system, I expect everyone should be able to handle this problem. And to finish this conversation, this right here is a feedback system. This system literally comes back into our system. So let's bring back our running man. Our running man's is ready to kick some, good old exams. He kicks an impulse. This 1 goes straight into the output. Straight into the output. However, it gets stored here. Now the next clock cycle, now this 1 is back here. So now we have this thing where it's literally an infinite cycle, or an infinite impulse response, or infinite response. So basically, we have, if we have a waterfall going here, this right here is a finite response. It's finite. You throw water here, it comes out. If we throw water in here, we don't even know what's going on, and this is where the stability equations come into play. So this right here is where we will experience the most unstable conditions, and I will show you what's going on with that. So let's see if I can teach you one concept. So there's one thing I want to get into everything. So with instability, let's think really simple. So if I were to tell you, let's say A and B. If A goes to infinity or to 0, then this total number, I'm just going to call it a Q or something like that. Q well, it's either going to go into infinity, which I don't know how you would build something like this that would go to infinity, or it goes to 0. You can just turn off your source. However, if you have your B term, the easiest way to go infinity is if this goes to 0. That's really easy to build, which is not good for this. It becomes unstable, or your bits start saturating, or you get some conditions that you don't like it, your op amp starts to rail to VDD or to ground. So this right here is what we consider our pole, and the A term is considered our zeros. So if you notice, we can relate this to our feed forward path and our feed back path. So this is where we can relate this feed forward path, our alpha, this is our A system, and this right here is our B system. So I'm going to establish something that you probably haven't seen, or maybe you have, which is, you know, H to Z is going to equal the output and input. So you've probably seen this in, you know, maybe 420 or your 220 classes, that transfer function you're looking for. Oh, what's the output with respect to the input? You know, you have your Bode plots. So if we were to replace this with the out of Z, I'm just going to do this, or Vn of Z, or Vn of n, don't worry about the Z. So this is the reason why I didn't want to show this concept, because you'll probably attack it at a later stage. But right now, we're just going to try and practically figure out what's going on. H to Z, there we go. This is usually what you would see in a Bode response. We have some response, our output over our input with respect to, you know, this also can be frequency or omega. So just to help you visualize this, which can relate to Y, Z, X of Z, and this will have to equal some, you know, actually let's split this up, H zeros and H poles is what I'm going to call it. So if we were to multiply this, and let's do this right here, so Y of Z, H poles, and this will be a function of Z. It's going to have X of Z, H zeros of Z. So don't worry too much about this, but we're going to relate this to, you know, Y of N and whatever coefficient, we're just going to call it HP, and X of N and H Z. So this right here is what we're going to try and look at. And actually, I'll show you one more concept before we move on. Let's go back to our little friend, the impulse response, or the system response, H of N, or let's do this, X of N, Y of N. And there's one thing I want to show everyone, and let's do this, Y of N is equal to X of N convolved with H of N. So if we wanted to go to, you know, a different domain, I don't know, okay, this is all going to sound confusing if you haven't gone through the Z domain yet, or Laplace domain. So this is a nice handy trick too, that you will realize in the next lectures when you discuss about the Z transform. Convolution in the discrete domain is also known as marker's dying. Multiplication in the Z domain, in the Fourier domain, or whatever domain you like to call it. So we're going to use this to our advantage. So notice that this right here is equal to, you know, our H there we go, zeros and our H poles. So we can just split this up into, you know, H zeros times H poles. There we go. So this right here, we can just split it up into X of N, H zeros of N, HP of N, Y of N. So we can split it up into these two types of systems. So this right here is going to be our zeros, and this right here is going to be our poles. There we go. And let's ignore this. So remember what happened when we have, like, you know, let's call it C of N, where if we take this and we convolve it with this, we convolve these two to get this output, and same thing with this. So by linearity, if we just ignore the Cn and we treat the C of N as H of Z, this is our new input into our next response. What I'm trying to get to you is, we can find our impulse response as zeros of n convolved with the poles. This right here is going to really help you solve some complex systems. Instead of solving for this crazy system, for this system, how do you find h of n? You can literally just solve for this, and we'll show you a couple techniques on how to approach this. Any questions? Man, this is hard. Oh, that's great. Feeling alive? Ready for that quiz? Oh, good. Alright, let's go. So let's see if I can bring you something. Let's go with red pen. So let's recall back our y of n plus alpha y of n minus 1 is equal to x of n plus beta of x of n minus 1. There we go. Thing right there. So the one thing we're going to solve for right now is, h of zeros. And from Dr. Stuber's class, h of zeros is basically, what we're trying to do with our inputs. So let's see if I can show you this right here. There we go. So the one thing we're going to show you is, well, with the h of zeros, we're taking an analysis of this term right here. So we're going to look for the zeros of this. So this is a really simple concept. I don't know if you've remembered from the lectures. And this is literally, you just replace x of n with direct delta. So all you got to do for this part is just replace all your x's with your direct delta, or sorry, not direct delta, your Kronecker delta, your delta function. You're just kicking the box. You're kicking the box and you're trying to figure out what your zeros are. So you kick your box, and what is, your final response. This can also be considered C of n if you really want it to be, special. It's bad. C of n. So you're looking for what this response is, and your C of n, or your h zeros of n, your impulse response due to, you kicking the box right here. You kick the box. What is the response of this box? Is going to be plus beta. And there you go. That's your first equation. Now you're already halfway done with this problem, and you're almost ready to find the total impulse response. So now the next thing we got to do, so the zero response is usually the easiest part, because let me see if I can turn back to some old page. This right here is literally a waterfall. You throw water in here, it goes straight into the output. However, the complexity comes right here, where we have some system that, well, it can go unstable. So let's do the following. Let's see, there we go. So to solve for the poles, we look for this term right here. So this right here is the zeros, and this right here is our poles. Just based on what we can see right here, our instability doesn't begin right here, it begins right here. So our B terms, whatever is closest right here. So we're going to take an analysis of this. So let's turn off all this. This is all gone. So now we're literally looking at the following system. Let's just do a C of n plus minus alpha. Draw your arrows to make sure you understand what's going on, how the water is going around in a circle. So let's just ignore this. If this is gone, this is zero. So let's just, well, not zero, but we'll consider it zero. So from what you've learned, this right here, sorry, I couldn't see this on camera. From what we've learned from, this differential equations, is there's this thing called, what we call auxiliary questions. So I won't go over the proof of that. You can go over that in the notes, which is basically we have these delays. We look at, our delays, and basically we say, okay, we have y of n and the y of n minus 1. The rule is we just replace whatever we see with lambda to the minus n. So I will do the following. You have 1 plus alpha lambda to the minus 1, which is equal to 0, or if you have OCPD, you can multiply this whole thing by lambda. This minus 1 comes from here, Or you have your own method, doesn't matter. Plus alpha is equal to 0. So this right here is considered your aux equation. I'm just going to call it aux equation. That's a funny looking name. But the point is, this is what you're looking for. Now you're trying to look for, you know, what lambda is equal to. Lambda is equal to minus alpha. And the one thing we learned about auxiliary equations is that there's going to be a general solution. We don't know what's going to happen, which is our, you know, let's call it y of n. It's going to equal some coefficient. We'll just call it c of 1. And remember, it's going to equal whatever our lambda is to the n. There we go. And let's put a unit step in there, because everyone likes a unit step. So all we do is place this minus alpha. Is it minus alpha? Yes. Actually, wait, let me see what I have right here. Oh, that's why I did that right there. So minus alpha and u of n. So this right here is, well, what happens when we kick something into the box. This right here is going to be our h poles. However, we don't know what this c of n, c of 1 coefficient is. So this is where we have to kick our box. So let's bring our running man. Our running man's coming, and we're going to kick this system. We don't know what this system is going to do. So let's, you know, bring out the big boot and let's kick the system. So now we have a 1. So at h or y, h of 0, we're going to have a 1. This is going to equal c of 1, and then we're going to have to make this one right here a 0, which is just going to give us a 1. And the unit step, well, that's 1 too. So that means easy. And we could go into another system like h of 1, but that's going to equal 0. We're just literally kicking the system. We don't know what it's going to do. But because of this, the simplicity and triviality of this problem, we've already solved for it. So that means your h pole is going to equal c of n is 1 equal to 1 minus alpha of n u of n. And now you are ready to convolve with this. So let's bring out the final step. And for clarity's sake, now we're ready to perform this operation. H of n is equal to h of zeros convolved with h of poles n. And now let's just do this brutal math. Oh my gosh, it's hard. Yeah, it's gonna get a little painful, but I will show you a quick trick. Well, actually, there's no tricks. It's all shown in the lectures. So let's bring out our h of zeros of n, which is equal to the delta function plus beta of d of n minus 1. And then our pole, well, pole is right here. Just put that right there. There we go. Now we can see that. It's going to equal, let's do this, the delta function plus beta minus 1 involved with minus alpha of n, u of n. And then let's use our trick. What happens when we convolve? Let's just use different colors so it's easier to see. What happens when we convolve this delta function with anything? We get the anything back at time n. Well, n is equal to 0, so let's do that right there. See right there. Just gonna get minus alpha n u of n. Now we're gonna convolve this. It's multiplication or convolve. What happens when we convolve this delta function with anything? We get the anything. However, at time n minus 1, times is a little beta factor. So let's do plus, because we are doing this factoring. We're not factoring. We're just multiplying this into different terms. So let's just do beta, the beta term, then minus alpha to the n minus 1, because we have this pesky little n minus 1 right there, u of n minus 1. There we go. And this right here is your total response. You can do some little quick tricks with this one right here, where if you wanted to factor this out, this right here can turn into beta, and we would have factored one of these puppers, alpha, and alpha to the, there we go, minus 1. So this would be your total impulse response. So now the next thing you're probably saying is, all right, now we have our impulse response. So now how do we check for stability? So stability is basically, what we're gonna do is, we have our system, h of n, x of n, and y of n. So if we kick the highest voltage we can kick into here, or number, or whatever you can say, let's call it voltage, is 1. So whatever we get right here, we expect that we can't get more power, or yeah, we can lose power, but we can't get more power than we put into it. So we expect that this has to be a 1. Because if I throw a 1 here, but we get like 3 or 5, then that's a problem. Unless our power system is you know, got higher power, but that would usually be that this number would be smaller, but our thing would be bounded to, like, you know, VDD and ground. This right here would be VDD and VDD. So we're literally putting the maximum, which is the impulse response. You're literally putting the max voltage that you can, and you're expecting this. If it saturates, that's not good. So the point is, we want to make sure this is equal to or less than our input. Yes, that's basically right. So how do you do that? Just look at this. So if you wanted to, you can do this the hard way. We're going to look at when our system's going to go, when it's going to blow up. So we're going to put an impulse response, and this right here is going to be a lot of math. I will show you the easier method. Let's go back to a previous discussion. There we go. So this right here is something you can easily plug into MATLAB, and this gives you like a nice natural response. You have your little alpha terms, and actually that's actually might be a good filter, depending on what you put for alpha. But let's recall this right here. So this is much easier to see, and let's get our piece of paper. So for the impulse response, we're going to kick something into our system. So here's the general rule of thumb. You just replace, there we go, let's bring that up there, plus beta x, not x, x1 minus alpha h minus 1. So right here we have our delta functions. Right here we have our actual impulse response, but we don't know what this is. You can literally take this and do whatever we did right here. Let me get that piece of paper right there. If you punch this term into here, then you get your actual response. Nothing in terms of your output, it's all natural. But this right here is a brute force way of doing it. But this is where it's easy to do it by hand. So if we were to, you know, throw a 0 into it, we kick our box. We kick our box at time is equal to 0, n is equal to 0. So we have a kick plus beta back of minus 1 minus alpha h of minus 1. So we're assuming that we have nothing that happened beforehand. So we're going to take this and we're just going to make the 0. And this delta function will only works at 0. N is equal to 0. Or this time, whatever is in here is equal to 0. So this term's out. So that means you get your first term. So that's a 1. So this is the maximum you can ever get. However, if you had some, you know, attenuation of coefficient, let's call it triangle, whatever. You're trying to figure out what to do with this attenuation. So let's say if it's equal to 1, then you can't generate more voltage. So you can see if you put a 0.01, then this goes to something bigger. You have something bigger than your actual input. This right here is unstable. You can't do that. So, or it saturates if you want to think about it. You create something VDD above. So when we think about it, we need to make sure this term is at least equal to or less than 1. So that's literally it. However, with this problem, it's going to be too simple. However, if you have like some complex system, like let's say this is gone. Let's say if you have these two terms, you would have to keep solving for h of 1 is equal to, let's do this, direct of 1 plus beta delta of 0 alpha h of 0. So we already know what this is. You would have to substitute this right here. So let's do this. This guy is gone. This guy is a 1. So your final term you'll have right here is plus minus alpha from that. H, put a triangle. And whatever that, yep, that's literally equal to 1. So there we go. So this would be h of 1. And you would keep doing this until, well, you get your natural response. But with this system, we're lucky that the impulse response is literally, if I were to draw it on a graph, if we take the time at n equals 0, it's literally going to be like this. It's going to do this, and it's going to attenuate. So this system was good. However, you might have some systems where the impulse response might be like, it might take some time. Like, well, actually, that's a bad example. Let's use the green marker. Your impulse response must start right here. However, it grows, and then it starts attenuating. So if you're doing computer assignment 2, this is the situation that you might be seeing. So you might not see it at n is equal to 0. You actually might see it at n equals 1 or 2. So you have to do a couple more iterations of this until you can see this. And you do have your R factor, so that's literally how you calculate for your stability thing. You can also use the Schwarz inequality, but the Schwarz inequality basically says y of n is equal to, let me remember, there we go, h of n, and x of k minus n, I think that's it. Infinity to minus infinity, and that's basically, you can do this. H of n x. The point is this x is 1, so all you're doing is you're looking at this. You got to make sure that this one stays less than your input, which is what if you put in 1. So that's how you would be able to do the computer assignment number 4, the second problem. This iteration shouldn't be that bad. It should be really simple, and you can prove your work using MATLAB. However, I'd like for everyone to try to do this by hand. It's really natural, it's really simple. I think you have a system where your input is actually not, you don't have a current input, you have a delayed input. So you're going to have, this type of startup rather than this type of startup. With this, you see this naturally with something with a delta function at the current time. However, in your MATLAB assignments, this is actually not here. You have an actual delay, and this right here is weighted right here. So that's it for the little review, and this was page 5. So good luck, everyone, and this is the study review for the exam. Hopefully this was helpful. This is a practical approach into looking at signals and systems.